All right. First, let me apologize for my technology today. My smart board's giving me trouble, so I'm gonna have to just do this on my computer. So my handwriting and my movements probably won't be as nice as on the smart board, but it should be just fine. First of all, I think everybody pretty much already knew what the word catalyst meant. Catalyst means, something that's going to cause a reaction rate to speed up. There can be a lot of different types of catalysts. We're just going to kind of talk about catalysts in general. And really, the way that a catalyst works, you're actually able to understand now. That you understand reaction profiles, those graphs that look like a hill, and that you understand mechanisms. If you look on your notes, there is a single step reaction. This one that I have up here first, it says uncatalyzed reaction. It's written on your paper first. That's the decomposition of hydrogen peroxide. And that decomposition actually is a one-step reaction normally. So you can see the uncatalyzed reaction, just decomposition of hydrogen peroxide, happens in one step. So two H2O2s break up. They get two H2Os and an O2. That's really how it works. But if we want to move into a catalyzed reaction, there's actually another way to get the exact same overall. Look at the overall here of this catalyzed reaction, and notice now it's two steps. Again, you're not coming up with these steps. I'm not going to say, tell me two steps that could give an overall equation of H2O2 making H2O and O2. That's not going to happen. What I'm going to do is give you steps or mechanisms like this and have you just sort of analyze them and look at them. And what you need to be able to do is look at a mechanism and, as we learned before, be able to find the intermediate if there is one, and now be able to find the catalyst. So much like before, if you think about what happened here between these two steps, if you added these two steps to give this overall equation, really what happened was there were two different substances that canceled out. This Br2 right here was a product and then it was a reactant. And so when you added the two steps together, you notice they crossed off, and that's why we don't see it as anything. We don't see it as a product or reactant in this problem. And then we also have, let me get a different color. We also have HBRs, two HBRs. If you see this HBr here, or these two HBRs, got canceled off by these two HBRs. So they were both canceled off. Now we've seen that a lot. We did intermediates, we showed things being canceled out. But again, there's a difference between an intermediate and a catalyst. A catalyst is something that is put in at the beginning of the reaction. Okay, so with the H2O2, they put in this HBr. This HBr here, what it does is it changes the steps of the reaction. It actually makes the reaction happen a different way than it happened before. And that new set of pathway is still going to result in the same final result. And notice what happened. So this HBr right here, it's the catalyst. Okay, this guy's the catalyst. Let me see if I can get a pen. I'm just going to use, wow, what the heck is that? Okay, hold on. I'm not sure what I did. You're laughing at me right now. That's all right. Okay, see, I told you this isn't going to go well, but good enough, right? So this is the catalyst, okay? You can see it was there at the beginning, and then it ends up showing up at the end. Okay, so catalyst, the beauty of catalyst is the reaction takes the catalyst, turns it into something else, and then at the end of the reaction spits it back out. So we actually have the catalyst back again at the end. We could use that catalyst over and over and over again. So it's really quite fascinating. Now there's also this Br2 here. We see the Br2 gets canceled, but it's not a catalyst. We already learned that this Br2 is an intermediate. Intermediates are produced during the reaction and then consumed again later on in the reaction. Remember, like our cookie dough. And so if you write this down, an intermediate is something that's first seen as a product. That should say product there. I'm not sure what happened. And then a catalyst is something that's first seen as a reactant. So you see that this one right here was the catalyst, because the first time we saw it, it was a reactant. Then we saw it as a product. Intermediates are first seen as products. So the first time we saw the intermediate, it was here as a product. So you can pick these out. You should be able to pick these out. A catalyst and an intermediate, both are going to cancel out in the overall equation. So that's how you know which ones to even be looking at. And then the catalyst is the one that's first a reactant. The intermediate's the one that's first a product. We can actually also look at a reaction profile. You have this on your paper as well. Remember from our discussion of reaction profiles that right here represents the potential energy of the reactants. Okay, down here represents the potential energy of the products. And then this is just sort of the path showing their energy differences as the reaction's happening. So here's when they're not reacting. Here's when they're moving towards each other. Here's where they collide, okay, right up here in the transition state or the activated complex. And then after they hit and react, this is them moving away from each other until you eventually get to an even line again, because now they're not interacting with each other at all. This reaction profile, the red line is representing the uncatalyzed reaction. Okay, the red line is representing the uncatalyzed reaction. Okay, the blue line is representing the catalyzed reaction. So if you take a look at this, what happens when you catalyze a reaction, look at what the activation energy was for the uncatalyzed one. Right? Remember we said activation energy is measured from the reactant potential energy line up to the tippy top of the hump. So this is the activation energy for the uncatalyzed reaction. This is not easy to do. There we go. Then if you look and take this line to the top of the tallest part of the blue one, look at the difference in the activation energy. It takes a lot less energy for the catalyzed reaction to occur, which is why it happens so much faster. Remember in those reaction profiles, we talked about the height of that curve tells you a lot about the rate. The higher the curve is, the more energy it takes, the lower the rate's going to be. Okay, the slower the reaction's going to be. If you have a short curve, that means the activation energy is really low, and it doesn't take much energy to get them to actually react. Now, you also may have noticed something strange about the blue one, in that there are two humps on this one instead of just one. And maybe you see why, maybe you're not seeing why, but take a look again at the catalyzed reaction. Remember, the catalyzed reaction happened in one step. So right here is where the two H2Os or two H2O2s collided. Okay, that's that one step. But notice the second one, the catalyzed reaction, is two steps. So this hump right here represents step one, where that collision happens, and this one right here represents step two. So a two-step reaction actually has two humps on its reaction profile. If it was a three-step reaction, it would have three humps on its reaction, or on its reaction profile. Also, we can tell one more really cool thing. Remember how we talked about fast step and slow step? Okay, take a look at the difference in the heights of these two activations energies. Hump number one's activation energy is about that high. Hump number two's activation energy is lower. Okay, it takes less energy to get number two to happen. So that's going to be a way to tell that step number two is faster than step number one. Remember our fast and slow step. If this was a reaction mechanism and we were being asked to do rate law or something, and the fast and the slow step, this one would be the fast one because it took less energy. This step right here would have been the slow step. And I feel like I'm writing this slowly, like so. And it's actually would be quite interesting. Now, I've never seen them do that on the AP test. I've never seen them give you a reaction profile in order to predict the fast and slow step, but I mean, maybe I should be a writer for the AP test, because that would be a fantastic correlation between these reaction profiles and reaction mechanisms. Because again, the mechanisms are the steps, the humps represent how many steps you have, and the taller the hump, the slower the rate of that part is, of that reaction. That's why the uncatalyzed one was super slow, because see how tall that hump is. Okay, so that's the basics of catalysts. And if you understand those basics, you should be pretty good with what you need to know. If you're not sure about any part of this, make sure you rewind it, go back, take a look at it before you go on and work on the homework.